By the way, we are broadcasting now. So, Joseph, the first problem that we're working on figure 40, and you can probably pause this or rewind or do whatever. Refer to figure 40, determine the total distance required for takeoff to clear a 50-foot obstacle. Here are the variables, and you'll see these in the upper left-hand corner of figure 40. OAT, outside air temperature, standard. Pressure altitude, or PA, 4,000 feet. Aircraft weight, 2,800 pounds, 2,800 pounds. Winds, calm. Compute, figure it out. Let's see what you got. Gentlemen here in the classroom. Show of hands if you got an answer. Solomon, well done. You two, you both got it? You good? Okay, all right. Waiting hero, that's fine. You guys knock it out over there. It's all right, take a minute. Remember, when in doubt, on most of these performance things, as well as in most POHs and AFMs, they're going to give you an example. So if you get stuck on something, you can look at the example that they list on the figure, and that can kind of get you pointed in the right direction on how to solve the problem. Capiche? I'm going to give you about another 30 seconds over here, table number 1. All right, here we go. Solomon, talk me through how to solve this problem. Talk me through it. What do we need to do first? Where do we start?
First, we need to start at the temperature.
Okay. What's standard? What does that mean?
Standard temperature is 59 degrees Fahrenheit, and I did not remember what the Celsius was.
Ah, well, you know what? If you know that much, take a look in the upper left-hand corner of figure number 40.
Oh, okay.
Oh, look at that.
Look at that.
So what do you got? That's 15 degrees Celsius. So, as we look down here at the bottom, we can see that they have chosen the identical temperature for us to start the example problem. Now what? Zane, what do we do next?
You draw up to, or you make a mark at 4,000 feet.
Okay, so you come up that line.
And you stop at 4,000 feet.
To 4,000 feet. Okay, you stop right there. Anders, what happens next?
Then you draw a line over to the reference line.
Okay, now we go to the reference line and we stop. Because remember, anytime that we come to that reference line, pretend it is a stop sign. Where people get in trouble on these things is by disobeying that rule. All right, so there we are. Elijah, what's next?
You find where you are, like you find 2,800, or you find, 2,800 pounds.
Okay, so right here we see that this is going to be our mark for 2,800 pounds, correct? So what do I do there at the reference line? Do I come down that little angle right there? Because that's kind of where mine shows.
Yeah.
Okay, so I'm going to follow that angle down to where?
To 2,800.
2,800, then what?
Then you go straight across.
Straight across to what?
To the next reference line.
Okay, remember I'm doing this freehand, and I get here and I stop. Okay? Gabe, what's next? What's next? The winds are what? Calm. So what do? If it's a headwind, I go down. If it's tailwind, I go up. But what happens if there's no wind? I go straight across. Well done. So in this example, no wind, I go straight across. And I stop. All right? Now then, Solomon, the very end of these instructions were to determine this total distance required for takeoff to clear a 50-foot obstacle. So now, young man, what do I do?
You follow the, I don't know what to call these bold black lines, but you kind of.
Do you see at the top of the example, Solomon? Do you see at the example where it says guidelines?
Guidelines.
Okay.
Good.
Okay.
You follow the guidelines direction all the way up until it reaches the end. Yeah, you follow the guideline all the way up.
Okay. So right there, what do we got?
1,500.
You got about 1,900 feet.
Okay. So what'd you guys get?
I got 1,900.
Okay. What'd you guys get?
I got like 1,100, because I thought, this could be wrong, but if you was at the bottom, I thought you just went straight across.
Okay. No, because at the bottom, this is like 25.
Yeah.
Okay. So if you go all the way to 50, you have to go all the way to that line. Okay. Now, here's the deal. As I look right here, I can see on this chart here, I have made an error. Because I was looking at the, and this is what's so hard about doing this, guys, just freehand with this pen, because I have nothing to lay my hand on to draw a straight line. However, as I'm looking at this right here, I can see two things. First of all, on my line right here, I needed to come down here just below this line at 4,000 feet. So I needed to come about right there. So I'm just below this line. As I come down here and I follow that to right there. Okay? So that puts me on that line right there. Okay? Now then, there's no wind. Hang on, I'm going to get rid of this line. There's no wind. So I'm going to come up here. That's about right. But I need to follow this because this line is halfway between these two guidelines, right? So I need to end halfway right there. Do you see that?
Yeah.
This is why drawing these lines is so important. The dot method, and Zane, I think I've shown you and Joseph that before. Andrews, I may have shown you that too as well in a different class, but that dot method works better for me if I'm having to freehand this sucker. So as I'm looking at this, gentlemen, I am looking at somewhere at about 1,800 feet. That's what I'm looking at. I'm looking at about 1,800 feet. Okay? Now, the book says the choices are 1,500 feet, 1,750, or 2,000. Those are the options that the FAA gives you. If it's me, I'm picking 1,750 because 1,750 is the closest to what I got, which was 1,800. Okay, and I'm looking. Correct answer is 1,750. Correct answer is 1,750. Let's do another one. Here we go. Refer to Figure 40. Determine the total distance required for takeoff to clear a 50-foot obstacle. Okay, so it's the same, we're looking to accomplish the same thing here, but the variables are going to be different. Here are the variables. Outside air temperature, OAT, standard. Pressure altitude, or PA, sea level. Takeoff weight, 2,700 pounds, 2,700. Headwind, calm. Winds are calm. You may now compute. 2,700. 2,700. Let me erase this stuff here. This is just tedious. I wonder if there's like a clear button on this thing. I don't know. All right, guys, compute.
Is there a obstacle?
What did I say?
50
Yes.
foot?
Yes.
Okay, yeah, I was just guessing.
Well, since I can't seem to clear that, here, I know how I can do it. Maybe.
Alright.
No, maybe not. All right, let me know when you got it. Thank you, Solomon. Thank you. You guys got it? You guys good? Elijah, good? Gabe, almost? Okay, Gabe, I'm going to give you another 30 seconds. No pressure.
Only about 6,000.
All right, here we go. Zane, how do I start this problem?
So you use your standard temperature of
Okay.
15 degrees Celsius,
Okay, so I'm going to start right there, correct?
and then draw that line up to the sea level line,
Okay, the sea level line is right there, right?
and then draw it across and stop at the reference line.
So I'm looking at this line and I'm looking at about right there. Is that right? Maybe a little higher, maybe just a little. Give me just a second
Can
here.
you not use a ruler on your computer screen?
I can't on this one. Okay, so I'm coming across here, trying to go straight across. Yeah, whatever. All right. All right, Anders, what do I do from here?
Your weight's 2,700.
Okay, so 2,700 pounds, so I find where that is, right? Now what?
And you draw your line down to it.
Gonna follow my line. Are you guys following the line here? Are you pretty much on the line or are you just above it?
It's like barely above.
Just, it looks like it's just barely above it. So I'm gonna look at this line and just go barely above it. Now what?
Then you draw straight across.
Straight across. About right there. All right there. And I get to that reference line and I
Draw straight across.
stop.
Stop.
Elijah, now what?
Now you draw straight across.
Okay, now I look at the wind. Make sure I'm doing the right thing straight across. Okay, all right. Gabe, now what?
And you draw between.
So if my margin is right there, what I'm looking at here is I want to come, I'm looking at my line here, guys, and it kind of looks like what I've done here, it kind of looks like I'm low right here. It looks like I'm low on this reference line. I'm having a heck of a time seeing that. See, it looks like I'm down a line. Give me just a second here because this is not making sense. Give me just a second, fellas. Let me get over here. All right, so I am fully a line down, so I need to be right there. Then I come down to here, 2,700. Then with this one, I come across, is it that one? It's right there. Okay, so there's my line there. Now I come across because the winds are calm. Okay. All right, there's that. Now what do I do, Gabe? So I want to finish, so I'm about a width below there. I want to finish about a width below here. So that's kind of where I am. So what have I got right there?
I got 1,230 feet.
Zane? What you get?
We got about 1,200 feet.
Okay. Elijah?
About 1,200 feet.
About 1,200. Okay. Gabe, what'd you get? See, I'm showing closer to 1,400.
Well, that is a pretty thick.
Well, I mean.
I know it's
the
hard.
lines are- you don't
Yeah.
have a ruler.
All right, so here's what the book says. Here's your options: 1,000, 14, or 17.
Dang.
Which one do you like?
I like 14.
What do you like? 14, 1,000. Elijah, what do you like?
1,000.
1,000? 14? Answer is 14. Correct answer is 14. See how hard these are?
Yeah.
Let's do another one.
Small.
Yes.
So the part that I have the most trouble with is that the weight and pounds part. Like, how are you supposed to make sure that you're coming down the right distance? Like, do you just like follow the line down?
So remember this, because I showed you guys this here before. So if you get to this second point here with like the weight, and for whatever reason I'm having a heck of a time here, because I can't get rid of those lines. Don't know why that's. Don't know why. Because I am completely out of that program. Boy, I don't want to close it. Okay, so let's say, for instance, okay, there it went for some reason. All right, so now let's look at it. So let's say, Elijah, that you have a dot right there. Okay? So what you want to do is you don't want to use the margin above or below that line, because you're going to get over here and you're going to be way down here. You want to say, okay, if this is halfway between these two lines, I need to be halfway at whatever weight it's telling me. So that's how you follow those lines. So it's a relative angle is what you're following based on where you show up on that reference line. So for instance, if on this top part here, let's just say that on this reference line, goodness, gosh, gotta figure that another way to draw. So on this reference line, if you're right there, you want to make sure that if you're down here, that's where you wind up here also. And it's hard because I've got a thick line that I'm using. So you want to use the average of the angle, not necessarily the distance from the line. Because that's the only way we've been able to get close to the right answers with how they do this.
Is there like a tabular method to do this? I mean, I know like in some planes you could just, it'll calculate your B speeds for you and tell you
Well,
how much runway you need with the.
in some it will, but the unfortunate part is that they're not going to let you learn how to fly an airplane in a $6 million airplane. You're going to start with something smaller, and you've got to learn the basics first, and this is the rite of passage to make that happen. I have got to start this over because I can't have these dots messing with me. Sure you want to leave? Yes, I want to leave. Okay, that's just going to be really icky. Here's the next one. Ready?
Yay.
All right. Determine the approximate ground roll distance required for takeoff. Determine the approximate ground roll distance to takeoff. Those are your instructions. Variables. OAT, 100 degrees Fahrenheit. PA, 2,000 feet. Your takeoff weight, 2,750. Winds, calm. Compute.
1,750.
I will only say these things one time.
Can I ask Siri the conversion from Fahrenheit to Celsius?
Nope. Remember how we did it in class the other day? This is one of the challenges of this class, gentlemen. You can't forget what we do from one day to the next. You have a landing distance chart, do you not? Take a look at that. Take a look at your landing distance chart and look at your temperature. About got it? Okay. About got it? All right. All right, Andrews, start us off. Where do we start here on this bad boy?
So
100 degrees Fahrenheit.
100 degrees, which is just below 40 degrees.
So let's call that, I don't know, let's call it 38.
I did 37.
Yeah,
Okay.
37.
All right, so let's do, well, 37 degrees Celsius, remember what I told you last time. 37 degrees Celsius equals 98.6 degrees Fahrenheit. So if 37 degrees Celsius is 98.6, 38 degrees Celsius is probably where we want to be, right? So let's find 38. I'm going to say right here and again with this I am. So it's every 2, so we're going to go right there. All right? Now, Anders, what do I do from here?
You draw it up to your pressure altitude, which is 2,000.
2,000. So I'm going to go just one dot inside of this. Does that look about right? Okay, now what?
And then you draw it over the reference line and stop.
Okay, I'm going to go to the reference line and stop. Well done. Elijah, what do I do from here?
You draw, or you find 2,700.
So here's 2,700, right? So where's 2,750?
It's two,
About right there, right in the center?
yeah.
Okay, so now I know that that's going to be right in the center. So now I bring this line down to about right there and,
Stop.
okay, then what?
Then draw a line across. Then stop.
Okay, and stop. Somewhere right around there. Right? Zane, what's next?
You stopped at the reference line. Draw across the wind since we don't have any,
Okay, since there isn't any,
and
let's
then
go straight
stop at the reference
across.
line.
Okay, all right. Now what do I do here, Solomon?
Then you draw upwards to represent the 50 foot obstacle. Wait, was there 50? Was there a 50-foot obstacle?
Gentlemen?
No, there wasn't.
No, there was
Okay,
not.
So you draw right across.
So we come straight across. All right, what'd you guys get?
About 1,100.
1,100?
1,100.
Gentlemen, table 2, what'd you get?
900.
900, that's going to be a little low. Gentlemen, table 1?
I got 1,000.
1,000? I'm looking at about 1150 right here, if I'm looking at this right. I'm looking at about 1150, book says. Your options here are, where am I? Right here. 1150, 1300, 1800.
I like 11.
1150
11.
is it. Let's do one more.
Is that actually how you actually say it?
I'm sorry?
Is that how you actually say it?
On the street.
Oh.
Yeah, because I got some street cred. So let's do one more here. Let's see how we do.
Mr. R, I know this is a very, it's just really random. Never mind.
Okay? So here we go. Refer to figure 40. Refer to figure 40. Determine the approximate ground roll distance required for takeoff. Ground roll. That is the part right up until the moment you rotate. Okay, so that's the ground roll. That is the part where you are in contact with terra firma. Determine the approximate ground roll distance required for takeoffs. The variables are as follows. Outside air temperature, 95 degrees Fahrenheit. 95 degrees Fahrenheit. PA, 2,000. Takeoff weight, 2,500. Headwind, 20 knots. Before you even start thinking about this, yeah, it's hot.
And that's
Pressure altitude's not too bad, 2,000 feet. Airplane's a little lighter, and I got a nice headwind. Am I going to have a longer takeoff roll or a shorter takeoff roll?
short.
Probably a little shorter. Let's find out. Kick it. One of the reasons that when I give you these figures and I put them on big paper is to help you count the lines so you can see the dots. Once you start actually using the computer testing supplements in the books next year, you'll see how much more difficult it is. Because even if you have a pencil that's not sharp, that can screw you up.
Really?
So it's a little different. Guys ready? All right, here we go. Gabe, start us off. Where do we begin? 95 degrees Fahrenheit, which equals approximately what Celsius?
I said 32 degrees.
I did 36.
Why'd you do 36?
I used this.
Okay. Why'd you use 36?
Because if
You said that's
37.
Thank you.
7.
Because I just said if 37 degrees Celsius is 98.6, and we know we got about just over 1.5 degrees is kind of the thing right there, 36 is going to get us closer to 95. You might have been a bit cool, but we know that already, right, Gabe? Okay, here we go. So we're going to start with this. Let's go 36 degrees. That's going to put me about right there. Oh my God, those lines. This is just horrible. Okay, now what do I do, Elijah?
You go up to 2,000 feet.
Up to 2,000 feet, and I know that it's the second from this one. So there's 1, 2, so there's that right there. Okay, now what do I do, Anders?
When you draw it over the reference line,
I come
stop.
straight across to the reference line and I stop. What's the weight of my aeroplane?
2,500.
2,500. Does this look right here, Solomon? Right here? You got to look up, son. You got to look up. Does this look right here? Solomon, you got to look up, son. Does this look right?
Yes.
Oh, thank you very much. So I'm coming here at 2,500. So now it looks as though, how many of you are just on top of that line coming down?
Yep.
About that? Okay, so I'm about right there. See that? Now what do I do, Solomon?
Then you draw down in between. Oh wait, sorry, I thought we were at the thing. Then you
I'm
go
at the
to
reference line and I
stop.
stopped. All right, Zane, now what do I do?
We have a wind of 20 knots.
Okay, so where do I find that?
Well, you want to mark where 20 knots is. and you
Okay, there's
wanna-
20 knots right there, right?
You basically want to do the same type of thing that you do with your weight.
Okay,
So you kind of bring it down until where you're halfway in between the top line and the bottom line.
well, but if my line is right here on this line, see where I am here?
Mm-hmm.
See where I am? So I'm just going to follow this right on down to 20, correct?
Sure.
Now what?
You draw over to the reference line and
And
stop.
stop, okay. All right, now what? What do I do here, Anders?
Since there's no obstacle, just draw right over.
Since there is no obstacle, I'm going to draw straight across this bad boy. Okay? Does that look about like where y'all got yours? Okay, here's your options. 650 feet, 850 feet, 1,000 feet. What are you thinking?
660.
I like it. There it is. There's your answer. Do you see the effect of that headwind? See how that helps us? Even though it's a pretty warm day,
See how
Yeah. Now, let me show you something else. Let's say that you had a pressure altitude on this thing of 8,000 feet. Let's say we had a pressure altitude of 8,000 feet. If you kept coming up this line right here, notice how this line right here doesn't even come across. So you're guessing at where that line crosses.
I meant you were too high.
This is it. Here's my point, is that in the summertime, we have pressure altitudes in excess of 10,000 feet here in Aspen. So what would we do with a chart like this?
I just wouldn't fly that day. Just that's too
Extend it.
dangerous.
I would just extend the chart.
No, I
Or
mean,
I would extend and like,
If this is your airplane, here's the thing. You could extrapolate what that is, but you're guessing at the curve. You're guessing at the curve. And so when you're guessing on performance tables, you're a test pilot. Let's just look at that. If that came across here, and again, boys, I'm just ballparking this. I'm coming across here to the reference line, and even if I come down here, 2,500, I come over here with this, I come down here. Even with that headwind, with a light airplane like that, we're still looking at about 1,500 feet. Here's my point. It was 650 feet with a pressure altitude of 2,000. With a pressure altitude of 8,000, it doubled. Nothing else changed. See where I'm going here? When you have that high density altitude, and remember, high density altitude, meaning that your airplane thinks it's higher than you actually are, that's the effect. It doubles the amount of runway that you've got to have, even with that headwind. If I put a tailwind in here with things like that, first of all, the Diamond only goes to 4 knots on the tail. We fly it up to 7 because we got a lot of runway up here. But even beyond that, you're extrapolating the data, and we have to be extremely careful.
are
Zane.
we flying at sea level in all of these situations?
No?
Well, our pressure altitude is our real altitude.
So pressure altitude is not real altitude. What
Okay,
is pressure altitude?
It's density altitude.
So how would you figure that? Do you remember the last thing we worked on before we started this? That density altitude chart? You work backwards from the end of where you are to find out what your true elevation is. So in this case, no, we're not anywhere close to sea level. Okay? All right. Stand by here. Okay? Refer to figure 35. Refer to figure 35.
one of the ones I just couldn't understand.
Oh, right, 35.
Oh, good Lord. Why do these things do this? You got it?
I don't have figure 35. Or wait, yes I do. I have that.
It's 40, 38, 35.
Is this figure 35? Is that?
This is bigger.
I really gotta get organized.
Oh, did you figure out how to change your order?
30. You're going.
All right, so what are we looking at here, gentlemen?
Cruise power settings.
So tell me how we might use something like this table. Solomon?
During mid-flight, we might want to see how much fuel will burn,
Mhm.
or
well, in mid-flight, we're going to do this in our pre-flight planning, right?
Yeah.
Okay?
During
It's
a
for-
cross-country flight.
It's
Mhm.
for mid-flight.
Yeah, en route. We call that en route. Okay? So we have climb, descent, and then the stuff that happens in the middle is en route. So with this is more what we would see en route. Okay? So we would go to this in our pre-flight planning to first of all determine what altitude am I going to fly, what is the forecast temperature for that particular day, because those things are going to affect the performance of our aircraft with regard to the amount of power that we can use. But then we can look and to say, okay, if I back that off a little bit and I lean the way I'm supposed to lean at altitude, to see what my fuel flow might be. Not only does it give me a fuel flow, but it's also going to give me a true airspeed. And what is it that I need to list on my pre-flight plan? My proposed true airspeed. So this is where we get it. Okay? So let's look and see what we have here. I'm going to look at this one first. So here, I've got in this box, this box, this box. What's the difference?
Standard day.
The temperature.
Temperature. Thank you very much. So the one on the left is going to be colder. The one on the right is going to be hotter. The one in the middle is just right. Thank you very much. I was hopeful someone would give me the Goldilocks thing there. Okay? All right, so that's what we have there. Why do you suppose they lead with the temperature? Because it's that important. Because it's all about the... Thank you very much. So if we look up here, we can also see another thing. At this one is 65% max continuous power. Why don't we want max power?
Because
It's hard on our engine.
Thank you very much. Very hard on that engine. It's hard on that engine. And in most cases, they only want you at max power for like maybe 2 minutes. And the only time is going to be on takeoff. Unless you have an expedited climb that ATC gives you somewhere, you know, from before or whatever.
you're trying to get away from the squadron of F-22s.
Okay. So this is kind of what we're looking at, because this is more of a realistic power setting that you're going to have in an airplane when you're going to go someplace. Okay? So, and again, for this aircraft, they're showing its full throttle at 2,800 pounds. So we just kind of take that with a grain of salt. Now, let's look at this. Tell me what we have in these columns.
Pressure, altitude, and indicated outside air temperature.
Okay? Pressure altitude's on the left. We have our temperature is going to be in that next column to it. Right next to it we have what? RPM. What RPM? Revolutions per minute. That spinny thingy out front, right? Man pressure. Is that like what kind of man pressure I'm going to put on something? Oh, manifold pressure. Oh, it's a little different then. Okay, never mind what I said. Manifold pressure. What kind of an airplane are we going to find a manifold pressure reading? Not, thank you, turbocharged. Yes, well done, Anders. Because if we don't have that turbocharge, but well, not necessarily, Anders. I'm just thinking about this. You're definitely going to have it in a turbocharged aircraft because you're going to have some other things on there. You're going to have turbo inlet temperatures that you're going to have, but in a constant speed propeller. Constant speed propeller is where you're going to find a manifold pressure. So those of you watching at home, I'm just correcting myself there, but that was good though. Okay, constant speed propeller. So you have that thing, it's got that blue handle on it, manipulate your prop, that's what it is. That's where you're going to find manifold pressure. Next we have what?
Fuel flow per engine.
Okay, so this is going to be your fuel flow, and it'll give you a pressure reading. This is pounds per square inch, and also your gallons per hour fuel flow. Then you're going to have what? What's TAS? What did I tell you? True air speed. That is correct. So in this, it will help you determine your true airspeed. So let's look at this, and let's, I'm sitting down here in the chair, and I'm trying to reach across this stuff, and hopefully I don't mess this up too much. So let's say on a standard day, let's go with 8,000 feet. Okay, so there's 8,000 feet. So what I'm looking at here is this. If it's a standard day where our temperature on the ground at sea level is 15 degrees Celsius, this is where we're going to be. So we would assume that at 8,000 feet right there, we may have, this is a pressure altitude by the way, so we'd have somewhere around 2 degrees Celsius at 8,000 feet. This is what they're showing us here. So if we look at that, that should give us an engine speed here with those throttle settings of 2,450 RPM, manifold pressure approximately 20.2, a fuel flow of what? Elijah? 11.5. And at that, it's going to give me a true airspeed of what? 161, correct? Let's say, for instance, your pressure altitude on a standard day was 9,000 feet. 9,000 feet. What would your true airspeed be?
182. Wait. Yeah, 180. 186, 187.
Not even close. If you were just at 8,000 feet and you were hitting 161, and you look at 10,000 feet and it's showing 163, what's 9,000 feet going to be? 162. It's going to be halfway in between, right?
Yeah.
That's called, don't speak, that's called interpolation. That is what we call interpolation. So we have one thing here, we have another thing listed here, but we need something here that's not listed. So we find what's in the middle. That's called interpolation. Good so far? Now then, let's see what that might look like at 8,000 feet. Here, when it's colder. We're going to wind up with a true airspeed of about 157. And if it's warmer than standard, we're going to wind up with something here about 164. Okay? Do you guys kind of see how you can look at this and kind of determine what your fuel flow is going to be? Here's the thing, if you look down at the bottom in notes, you'll see notes 1 and 2. What does it say, Zane?
Full throttle manifold pressure settings are approximate.
Okay.
And shaded area represents operation with full throttle.
Okay. So, shaded area represents operation with full throttle. Well, look at that. Look at what happens with a pressure altitude of 16,000 feet. Take a look at that. Okay, buddy. All right. All right. Andrews, see you, buddy. So let's take a look at the standard day and look at 16,000 feet. Take a look there at your settings now. With this, in order to get that 2450 RPM, you're going to have to go full throttle. And that's going to give you a manifold pressure of 16.1. And then as you look at that, you're going to notice that your fuel is going to be less. Why are you using less fuel at 16,000 feet?
Because because there's less air
there's less
resistant
air.
from the molecules.
And there's less air going into the engine.
Okay, good, good. Less air, so what does that mean that I need to do?
You need to turn down the fuel.
I need to lean my mixture to get it working properly, and when I do that, I can use less fuel.
And you don't drain the
And there's
engine.
less air resistance too.
Okay, that's part of it as well. Elijah?
So when you're at a higher altitude, you have to be at full throttle, but the RPM is 2,450, like the entire other thing. Are you still putting more stress on your engine because you're at full throttle?
It's a good question. Yes, but there again, a normally aspirated engine, because again it shows this tops off at 16,000 feet. So this is basically saying that 16,000 feet is about your service ceiling here for this airplane. A turbocharged aircraft is going to be, well above 20. And so with that, and the reason that I say that is this, is that with this airplane, you're probably going to have this airplane more at full throttle. But when you do that, this is where the only way that you're winding up with those RPMs at 2450 is because of the fact that you have a constant speed propeller. If you didn't, that RPM is really going to start to drop off. So like with the 172 without a constant speed propeller, you'd start to see then your RPM really start to take a dive. And the other thing is that with that, trying to hold 16,000 feet, what's your angle of attack probably going to be? So it's going to be a little higher angle of attack to kind of hold that. It's going to be draggy a little bit, which is one of the reasons why your true airspeed is actually going to be less than it would if you were flying at a pressure altitude of 8,000 feet. So with this, you're going to save fuel, almost 2 gallons an hour, which that means something. So you can extend your range, but you're going to go a little slower. So you kind of have to do the math on that and just see what's worth it. Okay? So can you kind of see how to use these a little bit? Let's find out. Here we go. Refer to figure 35. Approximately what true air speed should a pilot expect at full throttle at 10,500 feet, 10,500 feet, with a temperature 36 degrees Fahrenheit, quote unquote, above standard? So what true airspeed should a pilot expect at 10,500 feet with a temperature above standard? I'm going to let you work on this a little bit. What say you? What do you think? Zane, what do you think?
Well, it's
What's the first thing we got to do? So first of all, what we're doing here, I'm going to try to erase some of this stuff. Which box are we working with?
10,000?
No, the big box.
Standard day.
I said it's warmer than standard.
Oh, so ISA.
No, everything's ISA. You've got ISA minus 20, ISA plus 20.
Plus
36, thank you very much. So we're using this box, right? Now then, What's the pressure altitude?
Pressure altitude is 10,000.
10,500. Do we have a 10,500 on the left?
No.
Nope. But we do have what? We do have 10,000. We do have 12,000. So let's go across here. And we're going to look at 10,000. So the true airspeed that it shows here at 10,000 feet is 166, correct? At 12,000 feet, it's 163. So our answer is going to be somewhere between 163 and 166, correct? Okay? So if we look at this and I ask you what it would be at 11,000 feet, what would your true airspeed be at 11,000 feet?
164.5.
164.5. You have a 3 knot differential, and if you divide that by 2, that gives you 1.5. Add the 1.5 to 63, that gives you 164.5. Okay, so you can see that from 163 at 11,000 feet, then it's going to be 164.5. What if you were 500 feet lower? What would it be?
162 point. No.
No?
Oh, 165.
165. 165, because if 10 is 166, and you just said it was 164 and a half,
Okay.
10.5, I'm going to put that at 165. Okay? Here's your options. 190, which by the way, that's miles per hour. 159, you're going the wrong direction. Or 165.
165.
165. Do you see how that interpolation stuff works, gentlemen? See that? All right. Get to know that. And I'm going to have you guys Wednesday, correct? Am I going to have everybody here Wednesday? Who's leaving early on spring break? I've got half my other class gone by Wednesday.
Oh, that's
Well, just, the way it goes, I
lucky
guess.
them.
I'm gonna be here Wednesday, and I might not be here Friday.
So, for Wednesday, we're going to be kind of finishing up here on cruise power settings. I'm going to be asking you some more questions here on this, on figure, whatever that is, figure 35. And then I'm going to be asking you questions on your landing distance. So just like the takeoffs that we did earlier here on figure 40 or whatever that was, we're going to do landing calculations for Wednesday. Well, the graph. You want the graph, not that,
Oh.
but the graph.
I
Like
missed
it's a
the-
little graph.
Do I not need to catch up Joseph now since he got the live stream?
He should be okay.
Would you like me to text him that?
Yeah, it's on there. So with this, it is figure 37. Figure 37. Okay? All right, guys. I'll see you Wednesday.
Thank you.
Thank you, gentlemen.